This is the Chem 1 lecture covering atomic history. So in Unit 2, you learned about classifying different kinds of matter. One of those classifications was as an atom. Now, this idea of an atom is fundamentally important to basically everything we do in chemistry. So we need to have at least an understanding of where this idea came from. We're actually going to start 2,400 years ago with this guy named Democritus. He was a Greek philosopher that one day as he was sitting around came up with this idea that everything was made up of these things called atoms. Now, atoms wasn't the actual language he used. He actually called them atomos, but that's the Greek word that ended up giving us this word atoms that we use today. He had this idea that everything is made up of these tiny, solid, undivisible particles. In other words, if you had a loaf of bread and you kept cutting it in half over and over and over and over again, eventually you would get it down to such a tiny piece that you could not cut it anymore. That was the idea of the atom for Democritus. Just like a lot of things around those times, the Greeks were obsessed with this idea of perfection, and their perfect shape was the idea of a sphere. So what Democritus gave us was these tiny, solid, indivisible, perfect spheres that he called atoms. And there was atoms that made up of everything. And that you couldn't get smaller than that. Now, Democritus had some fairly influential rivals, most notably another philosopher named Aristotle, who proposed counter-arguments to Democritus's ideas. And because those other philosophers were more influential, they had more connections, they had bigger followers, it's their ideas that actually were advanced, whereas Democritus's idea of the atom fell to the wayside. In fact, it was basically forgotten for about 2,200 years, and it kind of sat in writings and was not a very prominent idea until this guy named John Dalton came around. John Dalton was a British school teacher who was also a scientist. Back in the 1800s, you were not just a teacher, you were also a researcher. Generally, people had multiple jobs because they had the ability and the intellect to do multiple jobs. So Dalton was working in a lab one day, and he was taking data on chemical reactions. He was combining things and seeing what they made. He was watching and observing gases and seeing how they compressed or how they expanded or how they interacted with the world around them. And so as he observed all these gases and he observed all these chemical reactions, he created the first true atomic theory. Democritus and Dalton's theory were very similar. In fact, they both had the same model, a perfect, indivisible sphere. So the actual model wasn't any different. The biggest difference between Dalton and Democritus was Democritus's ideas, the Greek philosopher ideas, were just that. They were ideas. There was no way to test it. There was no way to experiment with it. There was no real way to prove that Democritus's ideas were real. Dalton came around and he took these old Democritus ideas and he created a scientific theory, something that is provable, something that is testable. So Dalton took the idea of philosophy and he turned it into real science. That's why we credit Dalton with the first atomic theory, even though the basic idea was thousands of years old. Dalton's atomic theory came in 4 parts initially. First, he said that all matter is made of atoms. Those atoms are indivisible and indestructible, so basically identical to Democritus's idea. His second part of the atomic theory said that all atoms of a given element are identical in mass and properties. At this point, they'd been discovering new elements, new fundamental pieces of chemicals, and Dalton argued that all carbon in every single chemical compound was the same. Every single carbon atom was identical. Now, 1 and 2 we now know to be untrue. We know that atoms can be broken down into smaller parts, protons, neutrons, electrons. We also know that there's things called isotopes, which are the same element that have different masses. So they're not identical atoms, even though they are technically of the same atom. We have carbon-12, we have carbon-13, we'll have carbon-14. We're going to get into the intricacies of how we know 1 and 2 are wrong here in the next few days, but you do need to know the 4 parts of the atomic theory. So we've gone over 1 and 2. Part 3 says that compounds are formed by a combination of 2 or more different kind of atoms. In other words, 2 or more different elements combined make a compound. And lastly, that when you do have a chemical reaction, that you're not creating any new atoms. You're not destroying any of your old atoms. All you are doing is you're moving your atoms that were already existing around into some new combination. So 4 parts to the first atomic theory. You need to know all 4. The first 2 you need to know are now wrong. 3 and 4 are still 100% true. And I say 1 and 2 are wrong. 2 is 100% wrong. But number 1, atoms are indestructible, as far as anyone can really do anything with. All atoms are indestructible, but they are technically now divisible. They always have been, but now we understand a lot more about them being divisible. So Dalton's atomic theory existed for about 100 years. It was originally put forward in 1803, and in 1897, another scientist came along by the name of J.J. Thomson, and he discovered a subatomic particle, a particle smaller than an atom. He discovered the electron, and he used something called a cathode ray tube, or CRT. You need to know how these different scientists discovered what they did. Thomson discovered the electron using a cathode ray tube. The details of the experiment you really don't have to worry about. I'll talk about them, but you don't have to really memorize all the different parts. Just know the scientist, their discovery, and how they did it. So Thomson discovered the electron using the cathode ray tube. The cathode ray tube was essentially a tube containing a positively and a negatively charged plate, which helped to separate all the different parts of the atom, or of this gas. And he then shot a laser out the tube that contained only the negative parts of the atom. Essentially, it was just this ray that when he put a positive or negative plate near this ray that was getting shot out, he noticed that the ray moved. And it noticed that it bent towards the positive metal plate and away from the negative plate. Now, using what you probably already know about magnets, you know that positive attracts negative, negative attracts positive, and like things repel. Plus charges push away other plus charges. Negative charges push away other negative charges. So when he saw that this ray bent towards the positive side, he knew that the ray had to be negative. He discovered that electrons were these negatively charged particles inside the atom. And so he took Dalton's old model, that perfect indivisible sphere, and he edited it. He kept the sphere, because it was the simplest, most elegant solution. But within the sphere, he put these little negative electron parts. And he called his model the plum pudding model. Plum pudding is a British dessert. Looks like that. It's essentially a pudding cake with a bunch of raisins inside. Well, Thomson used that as a model, and he created essentially a giant cake of positive charge, and inside all that positive charge, he put these tiny little negative raisin pieces, plum pieces. So that's where it gets the name from, plum pudding model. It's essentially a giant ball of positive with little negative plums, little tiny raisins thrown in there. So we started with philosophy with Democritus. We've now covered the introduction into science with Dalton and the first subatomic particle with Thomson. Which brings us to another scientist, Ernest Rutherford. He discovered the nucleus. So, Thomson put forward his experiment and his discovery in 1897. Rutherford was coming along in 1911, and he did his own experiment. He took another laser, another beam, and he took a very, very, very thin piece of gold foil. So essentially just a few atoms of gold thick. Incredibly, incredibly thin. And he shot a laser at that gold foil. And he put a sensor almost all the way around the gold foil in order to detect what happens to the laser when it hits the gold foil. Now, Ernest Rutherford was testing to see whether or not atoms were really solid. If they were, then every single bit of the beam should get bounced backwards. Some direction, right? So in some way, shape, or form, oops, let me undo that. In some way, shape, or form, every bit of that laser should have been bounced back if the gold foil was truly solid. And when he did his experiment, he set up his detector, he did in fact see some knocked back. So he saw that there was some level of collision between the laser beam firing forward and the gold foil itself. What he didn't necessarily expect was that a lot of the laser, in fact, most of the laser, made it all the way through the gold foil, which shouldn't happen. If an atom is truly solid, there's no way that laser should have gotten through the atom. Two solid things colliding, bounce off each other. Which means this idea that the atom is this perfect sphere that is solid wasn't true. So he proposed his own model. And what he said was, well, since I know this laser went through, most of the atom has to be empty space. Because most of the laser went in and right out the other side, untouched. There has to be a lot of empty space inside that gold foil. However, in order to explain the fact he did see some deflection, both back and off at random angles, there had to be something solid there. So he proposed this very small, very dense piece in the very, very center. And he called it the nucleus. So he had a positively charged center in the very center of his atom with a bunch of empty space around it. Now, Rutherford had to create his model, but also take in what Thomson had discovered, had to take in the fact that they knew that negatively charged electrons were a part of the atom. So in order to explain his experiment and explain what they saw with Thomson, he said, well, my center is very positively charged, and in that negative space, the electrons are just flying around all over the place, completely randomly, attracted to the positive enough so that they stay within a certain area, but not so much that they just fly into the center and combine with the positively charged nucleus. So he had an empty space model, a positively charged center with a bunch of negatives around the outside. That was Rutherford. He discovered the nucleus using the gold foil experiment. Which brings us to another scientist by the name of Niels Bohr. Now, Niels Bohr actually put forward his model just a couple of years after Rutherford did. So Rutherford put forward his model in 1911. Bohr put forward his in 1913, so just 2 years later. And his model answered one very, very important question that Rutherford didn't quite answer with his. In Rutherford's model, there was nothing to explain why the positively charged center, the nucleus, didn't cause all of the negative electrons to just fly into the center. There was nothing there. Rutherford just said the electrons fly around, but they never go to the center, even though there should be this attraction between positive and negative. Now, Bohr proposed his model by looking up. He looked at the planets, so his model became known as the planetary model. We know that Earth doesn't fly off into space because of the gravity of the sun. So we know there's an attraction between the sun in the center of our solar system and Earth. That's what keeps us within our solar system. Obviously, they understood that gravity really didn't have the overarching effect in the atom. They knew it was positive and negative charges. But the reason we don't go flying into the sun, even though there's a huge attraction there, is because we're constantly moving in an orbit. So Bohr looked at the planets and used them as inspiration to try and explain why electrons don't fly to the nucleus in the same way that we don't fly straight into the sun. He set his electrons on discrete set orbitals, pathways, around the nucleus. He didn't call them orbitals yet. That came a little bit later. He just said that there's electrons that orbit in a set path around the nucleus. And those different paths correspond to different amounts of energy. The more energy you had, the farther away from the nucleus you were. So his level 1 would be the lowest energy, and moving up and up and up, and there was an energy level 4 and an energy level 5, so on, so on, and so on. Basically, he just modeled the solar system at the atomic level. So he tried to explain the flaw in Rutherford's model, that there were these pathways that ensured that even though there is an attraction between my positive and negative parts of my atom, they don't go flying straight into the positive. They're constantly orbiting, which keeps them at a set distance. In the same way that we are constantly moving around the sun, and that's why we don't just go straight into the sun. So this combination model of Rutherford and Bohr lasted another 7 or so years, but as they started to experiment more and more with atoms and their precision and their tools got a lot better, they started to notice some discrepancies. Ernest Rutherford showed or started to guess that there's these extra parts in the nucleus. They were looking at masses between different kinds of atoms, and they started to notice that there was an issue with an atomic number, which we'll talk about what that is a little bit later, and its mass. There was this weird unknown mass somewhere in these atoms. So Rutherford had a student, James Chadwick, and he tasked Chadwick with going and discovering these neutral particles that had to be living somewhere in the atom. Now, Rutherford had some guesses for where they were. Rutherford actually did guess correctly that in the nucleus, there isn't just positive charges, there's also these neutral charged, well, there's no neutral charge, these neutral particles that didn't have a charge but did contain mass. And he tasked Chadwick with going and discovering it. Don't really fret about understanding his particular experiment. It was a little chaotic and a little crazy. Suffice it to say that he used a source of radiation to shoot protons, those positively charged particles, at atoms and measured what came out the other side. What he saw was that when his radiation hit these atoms right here, the beryllium, they shot out a particle. When they took a positive and a negative plate and put it on either side of this new radiation, they saw that it didn't move. The radiation that came out didn't bend like Thomson's did. It didn't move up to one side of the plate, which told the scientists, hey, this radiation must be neutral. So they identified that there's this new particle coming out of these atoms. They then angled that neutral radiation at this particular compound called paraffin, which is essentially this compound that's very, very high in protons. And they did it to ensure that these neutrons hit the protons directly. And then at the same time, they measured what was coming out the other side. And they identified that after this radiation passed through the paraffin, it wasn't neutral anymore. Now this radiation was made up of positive charges because they bent away from the positive plate. So before it hit the paraffin, it was neutral. After it hit the paraffin, it was now made up of protons, which told Chadwick that the mass of this neutral radiation was roughly equal to the mass of the proton radiation. They knew, because the neutrons replaced the protons, that they were about accurate. They were about even. So Chadwick was able to support this idea that not only are there protons in the nucleus, there's also neutrons in the nucleus. It kept Rutherford's experiment accurate. The nucleus was still overall positively charged, but there's also these neutral pieces that give the nucleus even more mass. So Thomson discovered the electron with the cathode ray tube. Rutherford discovered the proton and the nucleus using the gold foil experiment. And Chadwick discovered the neutron. So there's your three parts of the atom: the proton, the neutron, electron, that we'll talk about in more detail in the coming days. Which brings us to our last scientist, a guy by the name of Erwin Schrodinger. Erwin Schrodinger was active at the same time as all of these guys. You might recognize his last name, the idea of the Schrodinger's cat. That was this guy, Erwin Schrodinger. We're not going to really get into the intricacies of that whole Schrodinger's cat thing here in the video. Talk to your teacher. They will be happy to explain it to you. But Schrodinger was not happy with Bohr's planet model. It just wasn't elegant enough for him. Now, Schrodinger was also a physicist, and he was a math person. So he started doing a bunch of calculations and setting up a bunch of equations and a bunch of formulas to explain a planetary model that works really, really well in 2 dimensions, but he elevated it to work in 3 dimensions, which is, obviously we live in a 3-dimensional world, so the atoms that make up that world have to also exist in 3 dimensions. So Schrodinger took Bohr's model from about 13 years earlier and updated it into using this idea of quantum mechanics. We're going to talk about all these different orbitals, all these different shapes in Unit 4. So don't worry about that right now. Just know that Schrodinger used a bunch of math and a bunch of equations to model a 3-dimensional atom, where electrons are most likely living in a 3-dimensional atom. They are living in orbitals defined by all these different crazy shapes, but notice you still got a nucleus in the very center. That's where your protons and neutrons live, but now instead of nice, pretty orbitals, Schrodinger says, well, there's an electron that lives somewhere in there. And there's an electron or 2 that lives somewhere in here, and 1 that lives somewhere in here. We'll talk about Schrodinger and all these different orbitals later. Don't worry about it too much right now. So there's essentially the history of the atom, from 400 BC with Democritus' philosophy of atoms, all the way up to Schrodinger's quantum mechanical model. Like I said, important information: know the scientist, know their discovery, know their experiment, and know their model. And you'll be good to go for that.